Welcome to the new video on Awgn, and in this video we are going to discuss about the Gaussian distribution. Okay, just to recap, what we did in our previous video was understand the Gaussian pulse, and then we had a hands-on on how to program a Gaussian pulse, and then we tried to understand some of the properties of the Gaussian pulse, like if you change the value of mu and sigma, how the pulse behaves, right? And we also had a bit of hands-on on how to generate the three-dimensional plots, how to analyze the three-dimensional matrix, and how to generate the animation in MATLAB. Okay, so now we'll focus on the random Gaussian distribution, okay, and not just the analytic formula, but actually in terms of the distribution. And if you notice that the distribution equation and the normal Gaussian function equation, they look one and the same. Okay, the only difference is that this is the distribution curve and not the normal curve, and it is also referred to as normal distribution, okay, in the literature. So to understand how this normal distribution looks like, let's go back to the Notepad++ and carry on with our programming. Okay, so now our next objective is to see the distribution of Gaussian Gaussian random numbers, okay, random numbers generated in MATLAB or in Octave. Okay, so now in order to generate these Gaussian numbers, Gaussian random numbers, MATLAB and Octave, they have provided us with a function called rand_n. Okay, rand_n, it is rand_n. N is for normal distribution. Okay, and so this is how the function looks like. Okay, so if I want to generate a set of vector, let's say I want to generate 10⁶ sets of random numbers which are distributed in such a way that they fall under the umbrella of the Gaussian pulse. So what I'll do is I will make this kind of a statement to MATLAB, and I will tell it that, okay, you generate a vector, it is 1 × 10⁶, but the numbers should be random in nature, and also it should have a normal distribution. Okay, and one thing to notice is that by default, okay, default it generates the data with zero mean, okay, with zero mean and unit variance. It means that the power of these random numbers will boil down to unity, and the mean of these random numbers will be 0. Okay, now if we want to see how it looks like, okay, let's run this code again and try to do a bit of we'll play around with this and we'll try to notice how things go. Okay, so I'll just clear the screen. And let's go back to our previous command. Okay, so this is my Gaussian generated noise. Okay, this is a Gaussian generated signal, and this is fine. I'll get rid of this plot, and now what we are after is the set of random numbers. Okay, now, okay, I have not stored it, so let us store it in some variable. Let's call it noise. Okay, another way of just playing around is that you can simply copy this line and put it into the console window. Okay, or the command window, it is called as like this, and it is going to give us the set of. So now I know if I see noise, size of noise, it will give me 10⁶. Now, as we have mentioned before, by default it generates zero mean and unit variance. So let us try to see what it is, whether it has generated or not. So when I say mean of noise, let's do mean of noise, and you can see that it's 0.001. It is very less, well close to 0, and as you keep on increasing the number of samples, it will converge towards 0. Okay, it will not be exactly 0, but very close to 0. And let us see what is the variance of this guy. Let us see the variance. The variance is 1.0012, which is almost equal to unity. Okay, so now we know that, well, this noise is having zero mean and unit variance. Okay, now let us see how it looks like. Let us see the distribution. So in order to see the distribution, the MATLAB has provided us with the function histogram function. Okay, so we can have the histogram plot. So what it is going to do is, the name of the function is hist, and the first parameter is the set of random numbers that we have generated, is the noise, and the next parameter is actually the how many bars that you want. Okay, so what is the resolution of the histogram function? So I'm saying that, well, okay, I want 100 bars. So what is it going to do is it is going to divide the noise. So noise is divided between certain range, okay, some range, minimum to maximum, and it is going to break that range into 100 different segments, and all the numbers which fall in that segment, it is going to display the probability of those. Okay, so the y is the probability, and x is the basically the bins that you have, or the segments that you have. And if you want to visualize this, you can visualize it using the function called bar. Okay, it will give you the bar plot, and you can say x comma y. Okay, so now let's run this guy and see how it looks like. So let's run this thing again, demo Gaussian. So this is what we have. Okay, this is how it looks like. Now as you notice, the range of this guy, okay, it is approximately between -3.8 to +3.8, and if you see that the curve is centered around 0. See, the curve is centered around 0. Okay, and we know that, well, the variance is 1. Okay, the variance is equal to 1, although we cannot directly visualize it from here. You can visualize the mean from here. Now how about relating this distribution to the analytic formula that we had derived before? Okay, so what I'm trying to do is I'm going to compare it with the analytical formula, and I want to prove that the distribution that we have got generated, it falls under the umbrella of a Gaussian pulse, okay, which we had generated before with zero mean and unit variance. And if I'm able to show that, well, it falls under the umbrella of Gaussian pulse with zero mean, unit variance, it means that the mu quantity that we had described before but we did not define it is actually the mean, and the sigma quantity is the variance, right? So let's do that exercise as well. So here the objective is to compare. Okay, so now my objective is to compare. So I'll just extend this guy a bit more and compare it with analytic formula, and prove that it falls under the umbrella of the analytic function. Okay, and it is basically, what I mean by it is the distribution. Okay, it falls under the umbrella of the analytic function, and show that mu is the mean and sigma is the variance. Okay, so in order to go to this objective, we have realized the first step. We have come to the first step, and that is to generate the set of random numbers. Okay, now I want to generate the analytic equation also using this. So what I'll do is I will simply copy this guy. Okay, I will simply copy this part here, and let's just comment this as analytic part, analytic derivation. And since we had done this exercise before, so I can simply copy it here, but there is a catch. Okay, now if you see here, I have taken x range between -10.1 to 10. I cannot take this x range. I need to take this x, right? This is x what I need to take, because I'm trying to compare with this distribution. So what I'll do is I'll replace this guy with x, and we know that, well, by default it says that you're going to have zero mean and unit variance. So I need to generate the pulse also with zero mean and unit variance. So I will say, well, okay, I will make this sigma is equal to 1. Let's say I have not defined sigma yet. Okay, we'll see that, but let's assume that sigma is some variance, and I am saying hypothetically sigma equals to 1. And let's say mu is my mean, and I'm making it a 0. Now if I am able to map it exactly on top of this guy, it means that, well, okay, mu is actually the mean and sigma is the variance, right? So this is how it looks like, and I don't think I'm missing anything else. So this should be sufficient for us. Now what we need to do is we need to have some kind of a plotting mechanism as well, right? So I'll move this bar point out of here, and let's have this plot the analytic formulas. So plot plot the comparative plot, comparative graphs, or show the comparative graph, doesn't matter. Okay, so let's run this thing first, to make sure that we don't have any error. Okay, so okay, now we have hit some problem here, and the problem is what it is saying. Okay, dimension mismatch. So it does not like, and I would suspect that it doesn't like x dimension mismatch. Okay, so here the idea is that I've got sigma equals to 1 and mu equals to 1, so it needs to generate okay, so mu count is also correct, sigma also looks correct to me, histogram is also correct. So okay, the dimension mismatch, I think it has come from here. Let us see the dimension of x range, and so let us see size of x. Okay, how the size of x looks like. Size of x, it is 100. And what is the size of x range? How it is distributed is 1 cross x range. X range is, okay, fine, it is overwritten, so I cannot do this exercise also. So what I'll do is I will simply copy this part and I'll try to execute. Okay, and then I'll have to do the debugging step by step, what is going on. Right, so this part is perfectly fine. Everything okay up to this point, right? Everything is fine up to this point. The problem happens after this. So let us come to this point first. X range equals to x. So what is the dimension of x? First, let us see the dimension of x. It's 100. And what is the dimension of x range? It should be around 201. Okay, but if you see, it is 1 cross 100 and this is 1 cross 201. So that is not an issue. This is perfectly fine, but I think most probably this could be the reason. So let me make this thing as a Gaussian Pulse 2, because Gaussian Pulse was already defined with certain dimensions which it is trying to override. Okay, so maybe this could be the reason. Let's try and run this guy again and try to figure out if that is the case. Right, so demo Gaussian, yeah, demo Gaussian, demo Gaussian, am I right? Gaussian. Okay, so it has not thrown any error, right? So the problem was with the naming. So remember that when you do the programming, right, you have to be sure about the dimensions of you if you're using the same matrix or the same variables again and again, especially in the matrix, right? So this matrix was already defined, G-Pulse, with it had a 3-dimensional matrix, and then I was trying to replace it by some other quantity, but here the range of these two guys, okay, the sigma and mu, it is only a unit dimension. It is not a multi-dimension. It doesn't take the value. It is not a vector. It is now a scalar. So this guy got confused and it threw the error. So if you just rename this into some different pulse, so this is like a different array now. So let us see the dimension of this guy. Okay, so if I say size of G pulse, what is size of G pulse? It is 14, right? And what is the size of G pulse 2? See? Okay, it is 1 cross 100. So now let us plot. So we'll use the same plotting function. We'll use this same plotting function. So let us do the plotting, and okay, and we will say hold on, and we want to do the overlap. Okay, so I think we have lost that x bar, but doesn't matter. So we'll call it x bar. I think it is bar. We will call it x comma y. Okay, now let's run this and let us see what happens here, and let's name this as a figure 2. Let's call this as a figure 2. Okay, right, now it has thrown another error. It says that, well, plot the matrix dimensions should match. Right, the matrix dimension should match because this guy, this is pulse 2. Okay, so now what I'll do is simply copy and paste these commands here. Right, now if you notice, something strange has happened here. and it is a bug. Okay, and I have intentionally produced this bug for you to understand what is exactly going on here. So let's see what is actually happening here. See, first of all, what I'm trying to do is I'm trying to overlap the Gaussian distribution, right? This is the Gaussian distribution with the pulse I'm generating, and I'm saying that, hang on a second, they're both supposed to be exactly same. If I overlap over them, then it should actually be under the umbrella. But if you see this, let me zoom this guy. It is of very low value. Okay, it is hardly visible. It looks virtually flat. So it means that there is some scaling issue here. See, you can see the Gaussian now. If I zoom it a bit, it looks like a Gaussian pulse, but well, there is no similarity between the two in terms of the scaling. So something is missing here. And what is missing is, okay, let us see the difference in the power. Okay, let us see the maximum or the minimum value change that we have. So let's see the change in the power. Let's clear the screen. Let's say the max of y. Okay, y is the one which is holding all the probability distribution. And let's say the max of g pulse 2. Max of g pulse 2. See the difference? It's huge. So does it mean that I simply divide this, I scale this thing down, or I just upscale this guy and I'm going to get the result? Well, okay, let us try and do that exercise as well. Are we able to see any change? So the idea is, what is the ratio of these two? Okay, the ratio, so either I need to downscale the bar plot or the probability distribution plot, or I will have to upscale the g-pulse plot. Okay, so but what is the ratio between the two? So let's see the ratio, difference in the ratio. Right, so I have 3939713 divided by, it is 0.39889, right? 0.39889. So what is the ratio? Okay, this is the huge difference. So let me try to scale this guy by this factor. Okay, let me try to scale this guy by this factor. So what I'll try to do is I'll multiply this. Okay, it is not copied. Okay, let me see whether it is copied. Yes, it is now copied. Right, so I will try to do this activity and let us see what happens. So I'll simply copy this plot function itself. Okay, just clear the screen and let us see whether we see any difference here or not. So let us see the plot. Okay, let's zoom out. Okay, it looks more or less same, but okay, so let me scale this thing further up and let us try to see whether we can see anything here. So as you can see, although this is not a very accurate way of doing it, but as you can see that it does fall under the umbrella of the Gaussian distribution, exactly falls under the umbrella of this. But in order to be more accurate, okay, what we need to do is we need to scale the bar plot by its actual. So this is basically the upscaling. But if you try to scale the bar plot, now you see here these are the rectangles. Okay, and so basically you need to divide the points with the area of this rectangle in order to scale it down. So another way of showing it is, okay, so let me get another figure here. Let me get another figure just to emphasize the point. So what I'm saying is, okay, now we are not going to scale this guy by this factor. It will remain as it is, but I want to bring this bar plot, I want to normalize this guy, and in order to normalize, okay, what I'm planning to do here is I'm going to divide it by the area. And in order to find the area of the rectangles, okay, because they are all rectangularly spaced, equally spaced, I need to find the base, I need to find the base, and I need to find the height. Okay, so height is already there inside y. So all I need to do is to find the base. So what is the base? Base is actually hidden in x. Okay, this is what the x is. So if I do diff of x, it will give me the width, okay, the step size. And if you see here, the step size is 0.98995. Right, so this is 0.98995. So I will copy this guy, and what I will do is I will do y times this. Okay, so here what I'm trying to do is each and every element of y, I'm dividing it by the area under which it is covered. And let us try to see the difference between the two. So let's run this guy again and try to see the difference. Okay. Okay. The bar plot, so I have got x comma y dot slash y times 0.095. So the value of y, you divide y by y times this value. Okay, so if you examine this plot, definitely there is something wrong here. And what is wrong is I forgot the sum. Okay, so what I'm trying to do here is I'm calculating the area across all the rectangles and I'm adding up them together. So that will give me the complete area under the Gaussian distribution, assuming that the plots are rectangular in nature, and then I'm going to scale the elements, okay, by this area. So if I do this, and so this should be now in good shape, and let us see now how it looks like. So okay, let's close this window first, and let's clear this and do the same activity again. And as you can see, we have got a nice umbrella, okay, sitting on top of the Gaussian distribution. Now there is also one more way of doing this, finding the umbrella, a better and more accurate way, although it is not visually it is visually difficult to figure out which one is better and which one is not better, but just for the sake of completion, I'm just showing you one more way of doing it, and that is by using a trapz function that is given by MATLAB. Okay, so I'll just call this as figure 4, and what I'll do is I will use trapz, T-R-A-P-Z. So what it does is it approximates the every rectangle as a trapezoid. Okay, and then it tries to calculate the area under the distribution, and then it is going to divide. So it's trapz x comma y, and if I do this activity also, so let's try to run this guy as well and see the difference, although visually we will not be able to see much. Okay, so let's do the trapz. Okay, it says trapz is undefined. Well, trapz is undefined because it is not trapz, it is trapz. Okay, so let's do this activity again. So just copy and paste. I'll just clear these guys. Okay, so let's see how the window looks like, the new window. So this is how the figure 4 looks like, and if you zoom this guy up, okay, so this is with the area as a rectangle, this is area with the area as a trapezoid, and this is how it looks like, although nothing much to choose from, but these are the different umbrellas that you can create to approximate the distribution. Okay, so so these are the different plots that we have got. Now what was our main objective? The objective was to find out that, well, if the umbrella falls on top of the distribution with sigma equals to 1 and mu equals to 0, then it means that my the quantity mu which I had not defined before, it has to be the mean, and this has to be the variance, because the distribution which I had generated here, it has a default unit mean and the variance. Right, so now let's play around with this a bit, and we will conclude this video, and then next we will try to look into the whiteness of the noise. Okay, what classifies noise as a white noise? So so here it says that, well, okay, we have the 0 mean, so let me make mean equals to 3. Okay, so what I'm doing here is, now I'm saying that I'm generating the random noise and then I'm adding an offset 3. So offset 3 means that I'm basically adding 3 onto the distribution, so it is going to shift my complete distribution, okay, by the factor of 3. And so here also I will do the same thing. So mu equals to 0, I'll make mu equals to 3, and now let's try to run this guy. Okay, so I'll clear this as a demo Gaussian. Right, so now you can see, oh, this is giving a better view of the approximations. So as you can see here, this guy has come with the trapezoidal approximation, right? Figure number 4. Figure number 3 has come by the rectangular approximation, and the figure number 2 has come by the scaling by the maximum value. Okay, the difference between the scaling. So as you can see here, if you try to calculate the mean square error numerically, you will see that, well, this guy has a more mean square error compared to this, and this guy has a least mean square error. And if you see the distribution, so now I have moved my distribution, right? I have got the mean is 3. So if you see the peak of the distribution is roughly centered around 3, and it falls directly under the umbrella of the analytic equation. So from this we can conclude that, well, the mu and the sigma are basically the mean and the variance of the distribution, and this is how the Gaussian distribution looks like. So in the next video, now we are going to focus on the whiteness of the noise, and I hope you have enjoyed these two videos. And so now from the next video onwards, we'll try to be more focused on the statistical part of the noise, and in the coming videos then we'll try to actually generate the noise. We'll generate the data, we will put the noise, and we will see the effect of the noise on our data. Okay, so I'll see you in the next video.